Hello from Chem Help ASAP. This is a reaction video. I'm reacting to a video put out by the creator Chemiolis, and he has a number of really nice synthetic organic chemistry videos on his channel. The particular video I'm reacting to is one about band sweeteners, in which he makes 3 different band sweeteners. I'm not going to cover all 3 sweeteners. I'm just going to cover one. It's in the image of the thumbnail. It's actually the middle one, the one that's orange. And we're going to cover the synthesis of 5-nitro, 2-propoxy aniline. And that's going to be about half of that 28-minute video. So let's go ahead and jump into this nice synthesis. All right, here we go.
Another sweetener I will make is 5-nitro 2-propoxy aniline. It is 4,000 times stronger than sucrose and was only used shortly in the US.
It's pretty amazing. This 4,000 times more, 4,000 times sweeter than sucrose, table sugar. It's incredible.
For it was completely banned by the FDA because of its toxicity. It is very hard to find information about this sweetener, even its...
Now, if you look at, so he's in a Wikipedia reference, and I love Wikipedia. It's a great starting place to look for material. But if you notice, it says on this one line, banned in the United States because of its possible toxicity. It's hard to take some of these things for at face value. You know, I kind of wonder, maybe a company had another sweetener that they didn't want to compete with this sweetener, so they found some evidence it might be toxic. But anyway, regardless, that was a decision and it was pulled from the market.
Synthesis. But it seems to be allowed in very tiny amounts in some countries. But it is hard to say if that's correct. It looks...
This is still maybe allowed in certain countries. So yeah, exactly how toxic is it?
It's like it isn't really used anywhere. This makes me really curious about it. So it will be the first one I will make. So to get started, I set up a flask in an ice water bath and drop in a stir bar.
Let's go backwards. This is an interesting stir bar. I guess I've seen this type of stir bar before, but you know, kind of a dumbbell stir bar. I'm used to just sort of the oval or egg-shaped stir bar. So that's kind of neat to me.
Stir bar. I add 85 ml of ethyl acetate as a solvent. I then attach a funnel. As a reactant, I add in 5.16 grams of 2-aminophenol.
So I'm covering, let's let that title go away. So this is, what is that, 5.16 grams of the 2-aminophenol. That is 47.3 millimoles. Just kind of remember that number, 47.3 millimoles. And if that's too hard to remember, it's about 50 millimoles. And so we're going to see that number come up a whole bunch, just to keep track of how much is present in the reaction in what proportion.
I then replace the funnel with a septum to perform the reaction under nitrogen, like is done in literature, but I'm not convinced that it's strictly necessary.
Yeah, I agree. This particular reaction should not be sensitive to air in any way, but it's not going to hurt anything. So, you know, it's just a precaution.
So I add 1 needle as an exit, and then a needle attached to a syringe with a nitrogen line.
So if he has nitrogen pressure in that syringe coming through that hose line, it will vent out that other needle hole and it will slowly purge all the air out, and he'll just have nitrogen, a nice inert atmosphere in his reaction.
Let blow nitrogen into the flask for a few minutes, and then slowly add 4.9 ml of acetic anhydride as a second reactant.
So that is, I'm kind of blocking this. 4.9 milliliters of acetic anhydride. That is 51.9 millimoles. So he has just about an identical amount of acetic anhydride as he does his 2-aminophenol. So about a 1-to-1 stoichiometry, which is what he needs for this reaction.
But it has all been added. I remove all of the needles and let it stir for a few minutes in the ice bath. Gradually, a white precipitate of the product forms.
So let's go back 5 seconds. Sort of look at the flask at the bottom.
We add 4.9 ml
it'll get
of acetic
cloudier
anhydride
in the bottom
as a second reactant. But it has all been added. I remove all of the needles and let it stir for a few minutes in the ice bath. Gradually, a white precipitate of the product forms. I then take it out of the ice bath and let it stir.
That's nice. It's always nice when you see precipitates like that. That means something's happening. Doesn't mean what's happening is correct, but at least something's, you don't want nothing to happen. You want something to happen.
At room temperature for 2 hours to complete the reaction. In this reaction, the amine of 2-aminophenol is acetylated by acetic anhydride, forming the corresponding acetamide. What happens is that the nucleophilic amine of 2-aminophenol attacks a carbonyl carbon of acetic anhydride, forcing one pair of bond electrons onto the oxygen. In the resulting intermediate, the carbonyl double bond returns, and the other oxygen takes up its carbon-oxygen bond electrons, and is kicked off. This immediately deprotonates the remaining protonated amine, of which the hydrogen-nitrogen bond electrons move onto the nitrogen. We are then left with the product, 2-acetaminophenol and acetic acid.
Now, I could be a little picky about this. And tell you what, while I'm being picky, let me back up and get my lights back on, because sometimes they turn off. I could be a little picky about that mechanism. And I only bring this up because someone watching this is probably saying, hey, you're a teacher. Don't you know that mechanism technically could be considered incorrect in some ways? I do recognize it could be incorrect. But we're watching an experiment. That mechanism is fine. It gets us from the starting material to the product. There's no reason to be overly picky about this. That mechanism stands on its own. Let's just keep going with the experiment.
After 2 hours, more precipitate has formed, and the reaction should be finished. When left to stand, we see the white product settle to the bottom. So to collect it, I set it up for vacuum filtration, through a glass fit with a filter paper on top.
Now, I will say, he likes using this glass frit, and I'm assuming it's the same one. It may not be the same one. And when I look at other chemistry content creators on YouTube, they also like glass frits. I'm very much a Buchner funnel kind of guy, so I like these ceramic funnels. Now, if this were a ceramic funnel, you couldn't see through the glass so nicely. I'd have to take the camera and show what's in the top because that ceramic is opaque. But I'm not really a glass frit guy in lab. I'm very much a Buchner funnel with the filter paper in the bottom filter plate.
I wash it out and down with some more ethyl acetate and let it dry on the filter for a second. I then set up a crystallizing dish and transfer all of the collected solid, which should be 2-acetaminophenol. The yield should be pretty much quantitative, but it's not necessary to dry it. So
this is, he's assuming he got 100% yield, and he does that because that's what the literature got. So just because we're keeping score here, he put in 47.3 millimoles of the 2-aminophenol. And so presumably, if he has 100% yield, he should have 47.3 millimoles of this material. That's important because we have to make sure he adds the right amount of reagents for the subsequent steps.
I assume my yield is 100%. For the next reaction, I set up a flask with a stir bar in a glycerol bath. To that, I add 25 ml of ethanol as a solvent and react it. And then 1.2 grams of sodium metal as a reactant.
Okay, we're keeping score here. So that's 1.2 grams of sodium. That is 52.2 millimoles of sodium. So 52, that's, if he has 47, that's about a 1-to-1 ratio, and that's about the limit of, or the minimum that he needs. He needs an equal molar amount, or equal molar amount. Sometimes you get confused on camera. Okay, keep going.
Before I continue with the next step, I have to wait for the sodium and ethanol to react completely. In this reaction, ethanol...
Yeah, so, well, let's finish what I was going to say, then we'll go back a little bit.
Reacts with sodium to form sodium ethoxide and hydrogen.
So he is making his base, sodium ethoxide, that larger compound on the left. And what this does is it releases gas. And you can see that gas formation. Let's slip backwards just a little bit. There we go. Watch around the neck of that flask and you'll see some vapor coming out. That's because it's fizzing because of the formation of that hydrogen.
Before I continue with the next step, I have to wait for the sodium and ethanol to react completely. In this reaction, ethanol reacts with sodium to form sodium ethoxide and
those vapors are probably ethanol vapors that are being pushed out, but they're being pushed out because you have this fizzing hydrogen gas forming in that reaction as the sodium reacts with the ethanol.
Hydrogen. Since the sodium is in big pieces, it will take a second for it to completely react. While that was ongoing, I started heating it to speed it up and also attached the condenser. I also took all of the 2-acetaminophenol from before and suspended it in some ethanol.
Okay, I want you to watch him pour this into the flask. He has that solid. He's going to kind of swirl it around to get a suspension of that solid, and he's going to pour it in his flask. And he does a beautiful job of this pour. He's going to pour it in. He's going to get it all in the flask. He's not going to get it all around the sides of the neck of the flask, which is what I would do. It's all going to go right in.
When all of the sodium has disappeared, I set aside the condenser.
Here
and
goes.
pour in all of the 2-acetaminophenol
Beautiful.
ethanol
Keep going.
mixture.
Beautiful. 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 It's always at the end. It's always at the end that it makes a mess. But he didn't make a mess. He just got everything right in the middle. That is a nice pour spout on that dish. But still, bravo. Great job.
I then reattach the condenser, and the reaction mixture slowly starts becoming more and more green. Now the next reactant.
Now, tell you what, before he gets to the next one, note he has that probe in the back. That probe is a temperature probe, and it's sticking into that dish that's on the hot plate. So he's keeping track of how hot this is. It's not too hot. It's not too cold. He has a temperature in mind. He hasn't told us what that is, but whatever it is, he's monitoring that temperature.
It's 1-bromopropane, of which I will add 4.3 mils slowly through the condenser. It becomes darker, and I then leave it to react for 4 hours at reflux.
So we can't see this on camera. Let's go back and watch it again. He's just dripping that in the top of the condenser, and the top of the condenser is off the screen. But if you watch, you can see the drips going through the condenser down into his flask.
Condenser. It becomes darker, and I then leave it to react for 4 hours at reflux.
It's dripping in. So that was 4.3 milliliters of bromopropane. That is 47.2 millimoles, so about 50. Again, he's adding one equivalent, a 1-to-1 stoichiometry of his reagents, because he just needs one propyl group to make his product.
In this reaction, 2-acetaminophenol reacts with 1-bromopropane in the presence of sodium ethoxide to form 2-propoxy acetanilide. The way it works is that the sodium ethoxide is a strong base, which can deprotonate the phenol.
Now, when I first saw this reaction, I thought, uh-oh, you might have a problem with that base deprotonating the nitrogen, that NH, instead of the OH. But I looked online, and indeed, that OH should be the more acidic proton, despite the fact that that's an amide, not a simple amine nitrogen. So anyway, this works exactly as he says. The base deprotonates the oxygen.
And form the corresponding phenoxide ion. Phenols are acidic in nature and can often be deprotonated by various bases. The resulting phenoxide ion is a strong nucleophile and attacks the carbon of 1-bromopropane adjacent to the bromine. The reason this is possible is because of the difference in electronegativity between carbon and bromine. This makes the bond polarized, meaning that on average, the electrons are leaning more towards the electronegative atom, in this case the bromine. This leaves the carbon with a partial positive charge and opens it up for attack by a nucleophile. This results in the bromine getting kicked off. In the end, we are left with the product, 2-propoxy acetanilide and sodium bromide.
So this reaction, whoops, hey, come
when
back
I come
here.
back
Come
after
back
a few
here.
hours,
I kind of lost control there. Okay, so this reaction, you would call this a Williamson ether synthesis. The final product is an ether. We made a new carbon-oxygen bond, and we did that through an SN2 reaction. We formed a nucleophile, that phenoxide anion, and it did an SN2 on the alkyl halide. Bam, we make an ether, Williamson ether synthesis.
the acetanilide and sodium bromide. When I come back after a few hours, a bunch of precipitated sodium bromide can be seen, and the reaction should be finished.
Always good to see those solids form. Precipitates are almost, they're a good sign something's happened, and of course, we want something to happen.
So take the flask off heat, and then set it up for vacuum filtration, to filter out the precipitated sodium bromide, which is...
So in the past, or in the previous reaction, this was filtered to collect the product. But now we want to remove the solids because our product is still in solution. So, sometimes you filter because you want the solid, sometimes you don't.
It's left on the filter as a white solid. I wash it out with some ethanol, and the product should be in the dark amber filtered. I set the flask with the filtered in a heating mantle and add in...
There's that weird stir bar. I don't like that stir bar, to be honest, but he's the one using it, not me, so it's fine.
The stir bar. I now start distilling off all of the ethanol to isolate the product. When pretty much all of the ethanol is gone, a dark liquid is left behind.
So he has evaporated off the solvent to get a residue. sometimes people say evaporate to dryness, which is, it doesn't mean there's water in there, but all the solvent's gone. So basically all the solvent's gone, and now it should just be his product.
To which I add some water, because the product is insoluble in water. I then leave it to stir to get the product to solidify. After a while sitting around, I also added a tiny bit of sodium hydroxide to it, just to help it solidify. And
that's interesting. So it's insoluble in water, but he added some soda, just a pinch, apparently, of sodium hydroxide to help it precipitate. That's, that would not have been my first inclination. That's pretty interesting that worked.
After a while of sitting around, it suddenly decided to solidify, and some crystals formed as well. I again set it up for filtration to collect the solid, and I washed it out with some more water. I then move it all to a crystallizing dish, and it is obviously not pure, evident by it being mostly brown chunks.
That brown color, I bet that's pretty nice stuff. It takes so little colored impurity to impart a lot of color. I think that looks pretty good. Now, I'm not saying it's clean. I'm not saying it's up to his standards, but color alone is not the best indicator. But it's what we can see with our eyes, so we always focus on color. But it's really, that may be just fine.
So to purify it, I will have to recrystallize it. So to the dish, I add some 25% ethanol and heat it to a boil. I keep adding more 25% ethanol until everything has completely dissolved.
It's interesting. He likes these big, wide evaporating dishes. I tend to be more of a beaker kind of person. I like a higher wall and a smaller surface area. He likes the higher surface area. In the end, it doesn't matter. It's what you feel most comfortable working with in lab and what works for you. But, there are different styles. People who practice chemistry, we all have our own preferences, and sometimes we do things a little differently, but as long as we get the job done, who cares?
I also add some extra water at the end, right up to the point it barely starts to precipitate out again. I then move the dish to the fridge to cool it down. After that, it had become milky.
Okay, so he says this is milky, which makes me think that there's no solid in there. This is a really common thing in recrystallizations from ethanol water mixtures, that instead of precipitating out as a solid, things tend to oil out. And so milky implies these are just fine oil droplets in here. Now, that's not a terrible thing, but he doesn't want this to be an oil. He wants it to be a solid because he's going to end up filtering it. So he's going to have to try to get this to solidify, and you'll see it happens pretty quickly.
But there was still some colored liquid sitting on top. But when I scraped it with a spatula, it all started to solidify.
So in these mixtures, even though it's oily, as soon as you agitate it, that disruption is enough to provide a site of nucleation, solids form, and once you get the solid form, all that oil fairly quickly solidifies. So, in no time, boom, he goes from oil to solid. You kind of like your solid to form slowly, but, you're mostly happy you got solid. Let's not be too picky. He wanted solid, he got solid. Okay, that's a victory. Let's move forward.
I also added some more water to make sure all of my product precipitated. And I then set it up for vacuum filtration again. I wash it with some more water.
Okay, it's that fritted funnel again now. Where's your Buchner funnel? But he's going to work in the fritted funnel.
And then dry it on the filter for a second. I move it to a dish, and I am left with a slightly off-white solid. That should be mostly 2-propoxy acetanilide.
Okay, so he has 5.7 grams of that material. It's probably wet, so he really doesn't have 5.7 grams of product. He's got a little bit of water in there. If you look at that is, and you work out the molecular weight and all, that's less than or equal to about 30 millimoles, just under 30 millimoles of material. So remember, we were talking about having 50 millimoles of everything. We started with 47.3 of the key starter material. Now he's lost some material. But where do you lose the material? Well, he just did a recrystallization. Anytime you do a recrystallization, you're going to lose material. The benefit is your material is cleaner, The downside is you're going to lose some material. It's just the cost of doing business.
The slightly wet yield turned out to be 5.7 grams. But again, I will not dry it, since it is not necessary. Now for the next reaction, I set up a large dish and put in a beaker with a stir bar, and then fill.
Look at that! That's stir bar. That's a stir triangle. I've never seen something like that. That's completely new to me.
Fill the dish with a mixture of ice and salt, which will make it extra cold, and reach to about minus 20 C. Then to the beaker, I first add 11 ml of 96% sulfuric acid, and then 10 ml of glacial acetic acid. I then leave that to cool down to minus 10 C.
So minus 10 degrees Celsius with that ice salt bath. That's frigid. So he's apparently sensitive to the temperature. He wants this to be a very cold reaction.
And I have added in a thermometer and covered the ice salt bath with some paraffin to reduce heat transfer to the ice. When it has reached minus 10 C, I gradually add in all of the 2-propoxy acetanilide. I help it mix with a glass stir rod, and when it has all dissolved and returned to minus 10 C, I prepare a mixture of 3.3 ml of 68% nitric acid. And
so let me get my cursor off there. That should go away. He's adding nitric acid and sulfuric acid. That is the nitrating reagent. So he wants to do a nitration of that aromatic ring. He has 3.3 milliliters of 68% nitric acid. If you go through the math, that's just over 50 millimoles of nitric acid. I don't have enough experience doing these nitrations, trying to control the amount of nitric acid, to know if you can literally try to do 1-to-1 nitric acid, if that stoichiometry is that sensitive. But he probably has about 30 millimoles of starting material, and he's got a somewhat of an excess of nitric acid in here.
5 ml of 96% sulfuric acid. I then very slowly drip in this mixture, while making sure that the temperature stays between minus 10 and minus 5 C.
He's really worried about that temperature. It could be that this product, if he lets this get too warm, it can do multiple nitrations, in which case he would put multiple nitro groups on his ring. He only wants one, so he's carefully controlling the temperature to make sure he just gets the reaction that he wants.
What happens in this reaction is that the 2-propoxy acetanilide is nitrated in the para position from the propoxy group, giving 5-nitro-2-propoxy acetanilide. This reaction should be done at these cold temperatures to prevent it from nitrating in multiple positions, as well as...
Yeah, so, he's avoiding a multiple reaction possibility here, so keep it nice and cold.
As preventing the hydrolysis of the acetamide. Acetic acid is only added to help dissolve the reactant.
So he mentions that he has an amide group in this molecule, and it's possible to hydrolyze that group. And there is a tiny amount of water, not a bunch, but a tiny amount. So he's trying to keep the molecule intact and keep it from reacting again while still getting the reaction that he wants. So he's kind of walking this line.
It is especially helpful in dissolving acetanilides. For the rest, it doesn't play a role in this reaction. What first happened is a reaction between nitric and sulfuric acid. The nitric acid is protonated by other strong acids, such as sulfuric acid, and forms the nitronium ion and water.
So that's the reactive electrophile. This is an electrophilic aromatic substitution. There's the electrophile in that green box, the nitronium ion, gets attacked by the ring.
Nitronium ion can be attacked by the aromatic ring of the 2-propoxy acetanilide, causing one pair of bond electrons to move onto the oxygen, and at the same time breaking the aromaticity of the ring, leaving behind a carbocation. This is quickly fixed by deprotonation of the adjacent carbon, of which the bond electrons move back into the ring to restore the aromatic ring. We are then left with the product, 5-nitro-2-propoxy acetanilide.
So if you look at that product on the right, we're just about at the final compound, except for he still has that amide group in the bottom right. So we'll take care of that in a bit, but he's getting very close.
When the addition was complete, I left it to stir for 30 minutes at minus 10 C. This is what it looks like, and when it is done, I take it out of the dish. I then immediately set up a beaker with ice and pour all of the mixture into it. I wash it out with some water.
So this idea of pouring a reaction onto ice, that is all over the older literature. I never liked pouring stuff into ice. I was more a fan of, I'll just cool the reaction and maybe drop-wise add cold water. But pouring a reaction onto ice to to quench reagents or cool the reaction. That's a really common approach, and here he's doing it.
And then mix it around. I dilute it with more water.
I always hated that ice in there. It's such a pain. You got these ice cubes. I don't want ice cubes in my reaction.
To force all of the product to precipitate.
So the product is not water soluble. It precipitates, and now he's got this. He's got this ice slushy. I don't know.
When it is done, I set it up for vacuum filtration to filter out the product. I remove the remaining ice.
So you got to remove that ice. Let's go back. Let's see those cubes come out.
I set it up for vacuum filtration to filter out the product. I remove the remaining ice and wash it with more water. I leave it to dry for a second and then move it all to a dish again. The result is a slightly yellow powder, but to purify it, I will recrystallize it.
Now, what I think would be interesting is how pure is this? Did he see any dinitration product? And there's a way you could figure that out fairly simply. If you took a TLC of that mixture, you might see multiple spots in there. You might not just see the product spot, but other spots that arose from different nitration products. Maybe he got a small amount of hydrolyzed amide in there, so he has a free amine, so he'd see that. So, there's a way to kind of take a peek and see how good that is. But, he just wants a product, so now he's going to recrystallize it.
I did earlier, though this time, I first dissolve it all into boiling ethanol.
He's still got that crazy triangular stir bar in there. That kind of fascinates me.
I then add water until it starts precipitating. I then make sure it is all dissolved by adding a bit more ethanol, and then move it to the freezer. It is all crystallized out into this mushy mess.
Okay, that's nice. Okay, it's all solidified. Now, I know it looks like that's one big mass of solid. There is a lot of liquid, all that solvent trapped within that lattice. So when he filters this, there will be some liquid in there to remove, and presumably that liquid will contain a lot of his impurities, leaving behind his much cleaner solid.
And I filter it all again, and add a bunch of water to make sure everything precipitates and to wash it out. Whatever is left on the filter, I immediately use for the next reaction, since it doesn't have to be dry anyway.
Okay, so he's not gonna weigh this. He's not gonna worry about drying it. So how much of that material on the screen does he have? Well, at most, he has the same amount of that material in terms of moles of what he put into the previous reaction. That was 29.5 millimoles at the most. So at most, he has 29.5 millimoles of that material.
So I set up a flask with a stir bar in a heating mantle and add some water and concentrated hydrochloric acid. I then add all of the wet product and wash it down with some water. In total, I have added about 50 ml of water. I then also add some more hydrochloric acid.
Okay, a little bit of acid, bunch of water, and a little more acid. And now we're ready to go, and we're going to hydrolyze off this amide group.
Which totals about 25 ml. I then attach a condenser, heat it to a boil, and leave it to reflux overnight. In this reaction, we are removing the acetyl group to return the amine in its hydrochloride salt. The way it works is that the acetyl oxygen is protonated by the acid, creating an oxonium that can undergo nucleophilic attack from water. In the resulting intermediate, the attached water is deprotonated by another water molecule to turn it into a hydroxyl group. Then, a free electron pair from one of the hydroxyl oxygens moves to make a carbon-oxygen double bond. Only 4 bonds are allowed on the carbon, so it kicks off the amine, which takes up the bond electrons, and with it, the rest of the molecule. The amine also immediately takes up a proton from the hydrochloric acid to balance its charge. And we are left with the amine product, but we are in an acidic environment. So the amine will deprotonate the remaining protonated acetic acid molecule and become the corresponding hydrochloride salt.
Okay, that is a classic mechanism for acid-catalyzed hydrolysis of an acid derivative. In this case, what's the acid derivative? It's an amide. So that's textbook.
When I come back the next day, everything has dissolved, and it has become orange, which is a good sign, so it should be finished.
It is orange. And he wants his product to be orange, so that's a good thing.
I then take it off heat and add an excess of a sodium hydroxide solution with a random concentration to neutralize all the acid and return the amine to its free base. I also add some ice to cool it down. The
So he just threw a bunch of base in this strong acid solution. And he's like, okay, let's cool it off a little bit too. He gave it a little bit of ice.
Solution becoming basic is evident by it turning cloudy, and the product settling out as an orange-red oil. I then pour it all onto ice to...
Again, the pour onto ice, I can't stand it, but it doesn't matter. It's working for him.
Cool it down and solidify the product. I allow it to cool down and wash out the flask with some water. When it's cold enough, I add a random amount of the solvent diethyl ether, which will dissolve the precipitated product.
Okay, so you saw how cloudy it was when he had it in water. That's because the product really is not very soluble in water. So he throws in a solvent that will dissolve the product, a diethyl ether. And so now he's going to have a two-layer system, ether floating on top, the aqueous layer on the bottom. And his product should want to dissolve into the ether layer on top.
I then move it all to a separatory funnel and wash out the beaker with more ether. I then bring the layers into contact and...
Okay, so he has shaken up this mixture. It's got ether in it. It has a little bit of base in there, excess base, water, salts from that neutralization, and his product. And remember, his product's orange, and he is seeing that top layer.
Separate them.
There's some orange there, but notice on the bottom layer, there's some orange there too. That could be product. So we're going to have to see how he deals with this, but he's going to drain this out at the bottom through the stopcock.
I extracted it 2 more times.
Oh, okay. Did you catch that? I extracted it 2 more times. So he wants to collect that ether layer now which is separated from the water layer, but that water layer that he drained down still contains orange stuff. So he doesn't show this. He does it off camera, but he'll dump that back into his separatory funnel and add fresh ether and see if any of that orange color will continue to be extracted into that fresh ether. So he gives it 2 more chances to extract. Now, you could argue if it doesn't extract after that, maybe the orange color that's left over is not his product. But anyway, he wants to get his product out if he can.
Times with ether. Then combined all the extracts in this beaker.
Okay, so that's now 3 separate ether layers combined there. He's going to throw in some sodium sulfate to dry everything.
To this, I add some sodium sulfate to absorb remaining water.
I'm kind of a magnesium sulfate kind of guy, but sodium sulfate does work okay.
I then set up a flask with a funnel and filter the solution through some cotton. I wash it out and down with some fresh ether, and then set the solution up for distillation to remove all the ether. When it's almost all gone, I attach a flask and pull a vacuum to make sure all the ether is gone.
So now he's evaporating off the solvent. That should leave his product, as well as possible impurities that could be in there. This isn't purified at this point, but he removes all the solvent.
When it's done, I am left with the product as an orange-red liquid. To solidify it, I pipette it all into a dish.
So he knows his product should be a solid. If it's pure enough, it should be a solid. So this is kind of a neat trick. He sort of spreads it out on this dish.
And then set it in the freezer. It then crystallizes to a vibrant orange.
And then puts it in the freezer. Bam! And he gets his solid. Where'd my lights go? Come back. That's kind of cool.
Orange solid that scrapes off easily. I put all of it into a vial, and the yield turned out to be 2.82 grams of 5-nitro-2-propoxy aniline.
So 2.82 grams, let me look at my cheat sheet here. That is about 14.4 millimoles of that final product. And if you compare 14.4 millimoles to what he started with, which was 47.3 millimoles, that is indeed an overall yield of 30%. And you might say, 30%? That doesn't sound so good. Well, he did 4 reactions. He did, he first converted the amine into an amide. Then he put on the ether, then he did the nitration, and then he hydrolyzed that amide. That's 4 reactions. And if you take the 4th root of 0.3, you get 70.74. So each of his 4 steps, on average, was about a 74% yield. That's not bad at all. Now, he doesn't have much evidence of purity of this material, but it's the right color, and it's a reasonable mass, so it's probably pretty good. He could take a TLC or something like that to show it. But anyway, he got it.
As a very orange solid, which is what it should be. This is a yield of 30% from the starting material, which is alright. I could not find any direct literature or even a patent for all these steps. So I took methods of similar molecules and stitch a bunch of papers together. Anyhow, now that the first one is finished, I'll make...
Okay, well, let's go back. Let's get that back on the screen. That's such a nice picture. So that's a reaction video to this synthesis. That was a great synthesis. A lot of that chemistry is exactly the type of chemistry that I teach in my Organic 1 and Organic 2 courses. And in fact, everybody teaches in the Organic 1 and Organic 2 courses. So thank you, Chemiolis, for making this video, putting it out there and sharing it with everyone. Thank you for your attention. And if you enjoyed it, please leave a like or subscribe. And I hope you take care and have a good day.